Thank you all. Welcome to the Python Meetup, to the Austin Python Meetup, the monthly meetup. We have two speakers for you tonight, and they are both related to data manipulation or data preparation towards some analysis mostly. One of them is more about analysis, the other one is more about the data preparation. So we're going to start with Yong Tang. He's going to speak about TensorFlow IO, and later Gunnar Kleemann is going to show how he uses graphs for cancer data analysis. So Yong, the floor is yours. Please capture the screen, present now, and go ahead and show us what you want to tell us about TensorFlow IO.
Okay, sure. Okay, can anyone see the presentation?
Yeah, we see it well. Go ahead. And you hear you well.
Okay, great. Okay, thanks guys for coming to talk. My name is Yong Tang. I'm a maintainer and CIO lead of TensorFlow project. I'm also a maintainer of several other Golang related projects like CoreDNS in CNCF and Docker in container ecosystem. By the way, this is my GitHub handle. If you have any questions, you can always reach out to me through GitHub. I should be available most of the time. In today's talk, I'm going to talk about data preparation and augmentation with TensorFlow. Specifically, I'm going to discuss about several things in the following order. First of all, I'm going to introduce TensorFlow and Keras. In case people are not very familiar with the area, I think a lot of people already know TensorFlow and Keras for machine learning. Then I'm going to talk about the problem of building a data pipeline in machine learning, especially in TensorFlow, which will introduce you with tf.data. And then I'm going to talk about TensorFlow IO, which essentially give you the extensions of data sets, format, and the streaming frameworks that allows you to read data from any sources and go into TensorFlow to apply your algorithm to build up your model, do training and inference. The examples I'm going to show will include reading data from database SQL queries such as PostgreSQL server, and from the streaming data sources like Apache Kafka. Before I started with the talk, I want to introduce you to a link which is a small repo I built up for giving talks. If you look into the, okay, let me show the web page. Okay, I think people can see this web page. Essentially, it's a small repo I used to demo for demo purposes. For today's demo, I have several tutorials you can follow through. Let me see if I can paste the link to chat. As you can see, there are quite a few tutorials. So if you follow through each tutorial, it's actually a Google Colab page. Okay, you can see that that's a Google Colab. And the good thing with Google Colab is that you can click through step by step and see the output immediately, just like you're running that on your local machine, except you even don't need to have a powerful machine yourself. The Google Colab itself is totally free, offered by Google. They give you the ability to run your program or run your machine learning program on Google's cloud servers for free, you can certainly just try to do things like running some of the code yourself. They give you an option of running on top of a GPU or CPU, and they even give you a free TPU to use. So I'm going to show you, I think everyone can see that. I'm going to show you that you can just click the tab and say run anyway. By the way, the code is totally open source, so there's no malware virus on the and the code can run. It's going to take some time. Okay, and you can click through to see the output. Yeah, I'm going to stop here because I'm going to come back to go through the tutorial, but just to give you the idea that in this page, in the previous page, the link I shared with you, you can follow through all the tutorials in Google Colab, and that I hope that's going to be helpful if you want to get a deeper understanding of the examples I showed in this talk. Okay, let me get back to the slides. Okay, before I get started, I want to discuss about TensorFlow and Keras. I think a lot of people already heard of TensorFlow and Keras, and many people are very familiar with that already. But it's just in case you're only getting into this field. TensorFlow is a machine learning framework. It's probably the most popular machine learning framework at the moment. TensorFlow allows you to do all kinds of machine learning tasks. It has a focus on speed and customization. If you're a machine learning researcher and you want to get into the field and you already have a lot of experience, you want to use TensorFlow to do uncomplicated things. On top of TensorFlow, Keras is another framework. Keras used to be a separate framework that's run separately, but since Francois was joined Google, Keras and TensorFlow has been combined into one. So if you download and install TensorFlow nowadays, you already have Keras available. So it's a part of the TensorFlow, which is called tf.keras under the TensorFlow framework. The reason you want to think about Keras is that Keras has a focus on high-level API for TensorFlow. If you're not a very advanced user and you're only just getting into the field of neural network, and you want to build some simple models or some even advanced models, but you just want to focus on application, then Keras probably is going to be recommended high-level API for you. Keras have very nice legal-like modular interface. It's very straightforward and very easy to use. And this is a great strength of Keras. So in this talk, later in the later slides, I'm going to show you why you want to use Keras if you just want to build some models and apply the model to your data or to your applications. The first example I'm going to show is a standard example, MNIST handwritten recognition problem. Let's say you have a picture which consists of digits, handwritten digits from 0 to 9. It can be any number, and you want to use a machine to detect that. So if you look into the right hand of the slide, you can see that's a standard MNIST data set with digits from 0 to 9. For this problem, it's a well-defined problem in machine learning, and it's probably an entry-level problem for everyone. To build a neural network and to apply your algorithm to detect this, to solve this problem, you need to have several layers. The first layer is input layer, which essentially is the input of 28 times 28 pixel image. The output you want to generate of your machine learning algorithm is a digit number from 0 to 9. So as you can see, that's a starting point of your neural network. In between the input layer and the output layer, you could fill in different layers. In this diagram, I showed only one layer, but of course, there's no limit in how many layers you can do. When you fill in those layers, you apply the model to your training data, the training data will give you, after the training, will return you back the weight of your model. If you apply the weight, calculated weight, you can do the inference, which will help you to predict if you have a new image of digit, and it will give you an answer from 0 to 9. So this problem by itself is very straightforward. I use that as an example because I want to show you why Keras is very easy for you to build a neural network. This is the model building with Keras for MNIST dataset. Of course, we have a Python meetup, so we are talking about Python. By the way, Python is the first-class system of TensorFlow and Keras. Keras is written exclusively in Python. TensorFlow, by a large chunk of code in TensorFlow is written in C++, although Python is the true first-class system. So you should have no trouble to use TensorFlow if you're familiar with Python. After you install TensorFlow, you can just import TensorFlow. The next several lines is just doing some simple data processing. We talk about MNIST dataset. MNIST dataset is a very standard dataset, and Keras already provided you a very simple tool. If a very simple value, which is tf.keras.dataset.MNIST, it gives you everything. With this dataset, it gives you a tuple of training and for test. For each set of training, you have X value and Y value. The X value is image, which is a 28 times 28 image. The Y value is a label, which, as we discussed, it's a digit number from 0 to 9, but in MNIST case, it's just an essential integer of 0 to 9. So at the next line is to divide the training data of image by 255 and the testing data of image by 255. The reason we divide by 255 is that the image is unsigned int 8 image, which could have a value of 0 to 255. We want to normalize the data so that we divide by 255. Now, the next step, of course, is going to be building the model. The model here is really simple, but it gives you an idea of why Keras could be an excellent tool for you to work on neural networks. The model itself is a sequential model, which means you add a layer at the end of another layer until it's reached to the output layer. The model has the first layer is a flattened layer, which flatten your input shape of 28 times 28 into a linear type of 768 values. It's just essentially flattened. The next layer is the standard dense layer. It consists of 128 units. The activation function for this layer is ReLU. The reason you need activation is that you want to remove the linearity because with linearity, you're not going to get great result, as some of parameter might be collapsed into a smaller number of parameters. The next layer is a dropout layer. The dropout layer is kind of like a random layer. For this dropout, it has a parameter of 0.2, which tells you that for this layer, for any node that's passing by, there's a chance of 20% that you're going the output will be good. So that's the dropout layer. And finally, you want to have a dense layer, which has the unit of 10. Why you want to have a unit of 10 is that because we are talking about a digit from 0 to 9. So of course, that's very logical, right? So the next probably is sorry, I'm wondering if anyone is asking questions. Is anyone asking questions? I heard some Some background. Okay, probably not. Okay.
So people are asking questions. You can actually look at them in the chat. They will wonder specific questions, but mostly they're chatting amongst themselves.
Okay.
We have 57 people, by the way.
Okay.
Now the only question that you may want to say is, what does ReLU mean?
Which one?
ReLU. It's in the previous one of the. It's the layer type.
You mean the
Yeah.
activation loop? Oh, that's a rectified linear unit. That's as I mentioned, that's an activation function for your neural network. When you build a neural network, you want to widen your neural network to be linear. If a neural network is linear, essentially your number of parameters will be collapsed into a smaller number of parameters. In order to remove the linearity, you add an activation function. ReLU is one of the activation function you can use. I think if you search for ReLU activation, you probably can get a better understanding. Maybe I can just show that to you. Let me just show this tab and give you an understanding. You can see that, right? So ReLU essentially is to take the input and change the value from change the value in a way such as the output will be in between 0 and infinity, but at the midpoint 0, it's going to generate 0, and before 0, if the input value is less than 0, it's going to be the same. So that's a shape you want to see. That's a ReLU, which is a standard activation function. You can also apply to other activation functions as well. You can see the time, the sig mode, those are the very commonly used activation functions. But yeah, that's just one of the ways for neural network to apply to neural network to remove the linearity, because the linearity is actually bad in your model. Okay. Okay, let's continue. So we discussed about building a model. In addition to that, we also need to provide a loss function, provide an optimizer, and the matrix. Here we just use a sparse categorical cross entropy for a loss function. The optimizer is Adam optimizer. You can certainly choose other things, but essentially this whole line, this whole line model.compile is all you need to build up your model, and your model is already in place. So if you check the number of lines, that's just pretty much like 10 lines of code. And you already have a model with several layers, with a dense layer of 128 unit, with an output layer of 10, which maps to the digit number from 0 to 9. So what next? Next is for training. When you do the training, all you need to do is to just call model.fit and pass your data of x.train and y x underscore train, y underscore train, which give you the training. That's all. And once the training is done, your model, the value, the variable model itself will carry the weight associated with your model, and now you can do the inference, like a model.predict, and it will give you the output for any data, and that's all you need for that's all you need to complete the whole application of building a model, apply the data to the model, and then do the training and inference. So as you could see, that's why I'm talking about the Keras, because it's just too easy for anyone not familiar with this field. Okay.
So Sherry is asking, what is in a high level you're trying to predict to predict your model to do? I can answer, but better you answer.
The predict model that predict essentially it's going to give you a vector of 10 vector of 10 values, and each value is going to represent the weight of the digit. Let's say if the weight associated with the digit 9 is close to 1, then essentially your prediction is that the picture's handwritten recognition is going to be 9. So that's the inference we are talking about. As I said, the input is a picture. The output is a vector of 10 that representing how likely each digit will be for this picture. Yeah. Does that answer the question?
Yeah.
Okay.
This answers well. Thank you.
Okay. Okay. Next, we are going to talk about the TensorFlow Data Pipeline, and that's actually the focus of this this meetup talk, because people say, okay, it looks like Keras is very easy, but when you are trying to apply machine learning models to your application, you realize your data source might not be so standard like MNIST, which someone already provided a data set for you. So you have to deal with getting the data source, doing the normalization, and even doing some pre-processing, which could be a tedious task. In addition to that, when you try to apply your model into production, you also have to think about the efficiency of your data pipeline. Why we talk about the efficiency? Because you want to make sure your I/O is not a bottleneck. I'm going to show in the next slide why I/O could be your bottleneck. As you can see this diagram, your I/O, when your I/O is trying to process data, your CPU and GPU is going to be idle. And unfortunately, CPU and GPUs are very expensive, which means you could be wasting a lot of effort just trying to wait. And this could be very pricey, especially if your pipeline is idle in cloud machines. I mean, in AWS or in Google Cloud. If you try to run some training or inference, and if your pipeline is not in good shape or pipeline is not a good fit, you can see your GPU is not doing anything, just waiting for the I/O to be ready. So that's why we want to have very efficient pipeline to improve the performance, such that our data can be delivered to GPU and CPU in chunks, so that while GPU and CPU are busy doing calculation, I/O is reading data as much as possible. TensorFlow has a standard data pipeline, which is called tf.data. For tf.data, it's part of the TensorFlow package as well, and it's a recommended way for data pipeline. There are all kinds of optimizations allows you to feed the data into TensorFlow in graph mode. I also want to briefly discuss about the graph mode versus eager mode. In TensorFlow, everything runs in graph mode. Graph mode means if you have a model, the way it runs is that TensorFlow will first compile your model into a graph, and in the graph, it will compile into a graph, and after that, it will run. This is different from the eager mode in TensorFlow. In eager mode, when you type a command line or type a model, the Python will offload the operation to a backend engine and get back to you in an imperative way. It's hard to say if eager mode or graph mode, which one is better, because they have different purposes. The eager mode is very easy to debug. It's just like an interpreter, like in Python in interpreter mode, you type a command and you see the result immediately. On the other hand, if you run your program in production, you may want to compile your Python code, and that's a similar comparison with the graph mode. Essentially, graph mode will run the pre-compiled code and allow you to see your pipeline running continuously without interruption. TensorFlow tf.data has also has a very easy to use interface. This is just a code snippet for reading data into tf.data. The data we are going to use is fetch MNIST, which is similar to MNIST, except it's showing the fashion logos. You can use tf.data.dataset from tensor slices to load the image and the labels. After you load the images and labels, you may want to see, okay, what exactly is tf.data? You can print out the element specification to see each element, what it is. If you print out like this one, you're going to see the tensor spec for the first part, that's image. You're going to see that's a 28 times 28 image of floating point 32. The second element, the second value in your tuple is actually a scalar, which you could see that's a 0D tensor of integers, 32-bit integer. This is the label, which essentially is a value in between 0 and 10. So that's a tf.data you're going to use. Now the question you may ask is what to do with tf.data. So how is that going to be useful for our training and inference purposes? Well, this line of code is going to show you how to feed the tf.data into model.fit. All you need to do is pass the tf.data into model.fit, and you can already do the training. Before that, you may want to do additional processing, like you may want to just shuffle your data a little bit so that your data is fully randomized. You also may want to batch the data. Why you want to batch the data is that if you don't do the batch, the data will be processed one by one, which could give you a lot of overhead in your pipeline. We go back, we want to see we want to fully utilize the I/O, CPU, and the GPU, but we also want to make sure each chunk of data is processed in batches so that the power of GPU can be fully utilized. So that's the tf.data we are talking about. The ease of use is that tf.data has full support for tf.keras, and it's also a first-class system in TensorFlow with model.fit. That's all you need, and it's very nice and clean. Next question is, okay, people may say, okay, I guess tf.data is easy, but I may want to do some additional operation. What should I do? tf.data provide you with many operations you can use so that your data can be pre-processed before it's fed into your neural network models. There are some operations. I'm going to list a couple of operations. The first is take operation, which essentially like a head operation that's going to take the first several elements. You can try it yourself to see what it is. You can iterate through with to see the image and label, and it's going to be very self-explanatory. A more important operation is the map operation. I think everyone should be familiar with map because map is a very fundamental functional operation, commonly seen in functional programming language. In Python, you have the map. In language like Scala or like Erlang, you also have the map. The map essentially apply a function to a data set. For example, if you have a list, you can apply a function to the whole. You can apply a function to the whole list one by one. You can also see the result. That's the function. The map function is very important, as I mentioned. Give you plenty of opportunities to manipulating, augmentation, and the preparation of your data before it's finally feed into a model to do the model.fit. So next thing,
Yong,
yes,
if I can interrupt, there are several questions that might be interesting to answer now before you go on. So
yes.
I see Tom is asking a question. Tom, you can unmute yourself because I cannot read and figure out the question from the long text. But before Tom will unmute yourself, can you unmute yourself?
I can
Okay,
try.
ask your question so he can answer.
Well, the question is, if you want to construct a pipeline and divide the data in logical batches that do not affect each other, so you can process them independently, that is somewhat obvious for the collection of images. But if you're dealing with the data that you do not understand yet, how do you do it?
I'm going to give you some of the examples shortly after in TensorFlow IO, say why TF data is not going to be enough, because TF data, as I explained, although it's part of the TensorFlow package, it only builds a pipeline. And by standard, it gives you ability to process the image. But sometimes you may have some other sources of data, and it's not going to be straightforward. So that's why you need an extension like TensorFlow IO to process that. I'll just show in more details in the following slide.
Okay, before you go, Gunnar has another question. He wants some clarification between eager mode and non. Gunnar, you can ask yourself.
Yeah, so I mean, this is pretty interesting, I think. I mean, that you showed like 10 threads versus 3 threads, or what looked like 10 versus 3 threads. I mean, obviously the hardware should be the same, right? So I'm just wondering what's giving you the difference between 10 and 3 threads?
No, it's not a 10 and 3 thread. It's actually if you, okay, you can still see the diagram, right?
Yeah.
The thing is, if you're going to read I/O, you want to make sure that I/O, while I/O is reading the input output, or the input is processing and reading data from some of the sources, let's say some storage like hard disk, or maybe from like cloud storage like Google Cloud Storage or like AWS S3. You want to make sure while at one side you're processing those data and waiting for the data to be ready, the GPU can do additional things. So if you look at the pipeline, there's no 10 threads. It's still just you make sure you're running into small chunks such that when CPU and GPU are running, because the I/O is typically very slow. When the I/O became available, they can be immediately consumed as soon as possible instead of waiting for all the data to be available.
I see. That's nice. Thank you.
Okay.
Okay, you can proceed now. Apologies, but those things are better clarified while people ask.
It's fine. It's fine. I think that's some of the questions many people encounter. That's why people ask why do we need TF data, and why this is even an issue. People just think sometimes people think, okay, we already have a data, but a lot of time your data, if your data is large, your data source could be from somewhere that's very slow to read. If you are from hard disk, the speed of data transfer from hard disk to memory is like, I think, I don't remember the
1,000
current.
times slower than memory, approximately.
Yeah,
Approximately.
I think, yeah. And in some situation, your data might be from a remote server, like from AWS S3. This is even more troublesome because a lot of time you have to wait for a long time before the data is loaded into memory. And if your data is too large, you want to make sure your data delivered in chunks so that it can be processed by GPU, because your storage could be large. It could be in hundreds of gigabytes or even terabytes. But when GPU is processing, that's normally in the scale of less than gigabyte. So there's some discrepancies between GPU, CPU, and I/O. So that's why we want to have a efficient pipeline to make sure the GPU power is not wasted, because the GPU is very expensive nowadays. Okay. The next thing I'm going to talk about is TensorFlow IO. Why we talk about TensorFlow IO is that while TF data give you a pipeline, TF data itself only focusing on pipeline, and they are not talking about, they are not focusing on anything about input format. They're not focusing on anything about other frameworks. So it comes to a question of people say, okay, I have let's say I have a solution. My data is saved in somewhere. Let's say Azure Blob Storage. It's saved as a file. How do I read that? Unfortunately, with just tf.data, that's it's not possible because tf.data, the focus is on pipeline itself. So what you need is a TensorFlow IO, which is the extension of TensorFlow, give you all kinds of data sets, file format, and file system extensions. TensorFlow IO is part of the TensorFlow organization, so you can consider it as pretty much official. Although the TensorFlow IO community is the community driven, it's sponsored by Google, but most of developers are not working for Google. We do have a couple of maintainers from Google Cloud, but that's but most of us are doing that voluntarily. We have different type of support for very different sources. We have support for data set, such as you can read data from BigQuery, which is a very big thing in Google Cloud. You can read data set from PostgreSQL. You can read even from some streaming frameworks like Kafka, Elasticsearch. You can also read things from Apache ecosystem like Apache Arrow. In addition to that, TensorFlow IO also support file systems. The file systems consist of Azure Blob Storage, which is from Microsoft Azure Cloud. In the past, the GCS, the Google Cloud Storage, used to be embedded into TensorFlow package, but we have some discussion. We decided in TensorFlow, TensorFlow will only will only embed a file system for host file system, which is your native file system, and all the extensions like GCS, Google Cloud Storage, will be part of the TensorFlow in the next release. So that's why you may need that if you want to interact with cloud storage. We also have different file format support. Like a package file is a very interesting file format that's used widely for some data analytics. The reason people want to use Package is that Package, there are a lot of tools allow you to do some queries on top of Package files. Unfortunately, TensorFlow does not have Package support by default. So in TensorFlow IO, we added the Package support. We also have a lot of audio format support, such that you can read those audios automatically. In TensorFlow, there's no audio format support. You can only have a very vanilla WAV file, which is very limited. And without TensorFlow IO, for any source, any data source, you have to do the conversion first. And I'm not sure it's worth effort to convert all your MP4 files into a WAV file, which is going to be super larger. So that's why you need to have the support for additional file format, file system data set, just to make your so that you can focus on building a model, trying to come up with a great algorithm to solve the problem, and leave those infrastructure issues behind. I'm going to give you one example about PostgreSQL. You should be able to see why it's a lot easy now with TensorFlow IO. As I mentioned, in my link I shared at the beginning of the talk, there are several tutorials. You can go through each one, and it should be self-explained, all the detailed steps you need. If you look into, for example, PostgreSQL's tutorial, you can see in Google Colab, the tutorial even build up a PostgreSQL server. So the server is actually running. And if you click through, you're going to see how you can process the data, read the data from PostgreSQL, and do some additional processing. and apply some functions like use a dataset.map functions, and eventually you should be able to have a dataset that's ready to be fit into tf.keras directly, which will save you a lot of time to do all the conversions. I'm going to speed up a little bit because it looks like we are a little bit running behind the time. So to install TensorFlow IO, you can just do pip install. That's all you need. And TensorFlow IO only depend on TensorFlow. So as long as your system can run TensorFlow, you should be able to run TensorFlow IO as well. For PostgreSQL, the first thing you need to is to construct your endpoint. This is very standard and common for if you work with PostgreSQL database before. You need to provide the username, password, host name, port number, and the database name, just like in the past, how you connect to a PostgreSQL. And then if you want to read data, all you need to do is calling a function and provide the query you want to query, and that's it. The result will be returned as a tf.data data set. As we discussed, you can continue your manipulation or transformation to use things like a map or filter or like a take or any operations applies to data set applies to tf.data can be equally applied here. At the end, you can just pass the data set to model.fit or model.predict to get the training or inference. So if we walk this through, there are only several lines you need to do. If you know how to construct a PostgreSQL endpoint, if you know your query you want to if you know the select query, that's all you need. Okay, so that's I'm going to leave more details in the tutorial. As I mentioned, you can follow through a tutorial, and it's very detailed, so you can go through line by line to see how everything works. Let's get back. So the next thing I'm going to discuss is some people say, okay, PostgreSQL, that's great. But sometimes people will say, I want to do some online training or online inference. And I have some data that's coming from different sources in a continuous way. What should we do? So first of all, depending on your sources, you may have data. If you're dealing with streaming data, you're probably going to save the data into some streaming frameworks like Apache Kafka. Apache Kafka essentially save the data in a sequential way. As data coming in, it will be appended to the end of your write-ahead log. If you read data, you can read data from the head, and as you read, the offset will be moved all the way to the end. That's the streaming framework most of the people use nowadays. Because it's so widely used for streaming data, so people say, okay, I want to apply machine learning algorithms and combine with Apache Kafka. So what should I do? Let's see how to read Kafka stream into TensorFlow with TensorFlow IO. As I mentioned, TensorFlow IO, one strength with TensorFlow IO is the interface is very straightforward, very easy to use. If you try to read data from Kafka, at the minimum, you only need to specify your topic you're going to read. The server is the Kafka server's endpoint you should pass. And you also, optionally, you can provide additional configuration, like this configuration, that's a fetch of a minimum bytes equals 2, which is related to how you deal with a fetch. You can put any configuration as long as it applies to Apache Kafka. And once you get the TF.io's data set constructed, that's all you need. If you pass the data set into model.fit, the whole graph of TensorFlow graph will just run continuously, fetching the data, do the training or inference. So that's all you need. And the interface is very clean and simple. I think we are running out of time already, but I want to summarize what we discussed in this talk. In this talk, we mostly discussed the ease of use of tf.keras and how to feed the data into tf.keras in an efficient way, and how to deal with the data source that's not very common for machine learning researchers. With TensorFlow IO, you can deal with data source. You can deal with many different data sources. That's very common in production, but not very common for pure machine learning researchers. If you try to build a production pipeline, you might be dealing Apache Kafka every day. You might be dealing with Elasticsearch. You might be dealing with some of the format like packet files, and those are things that TensorFlow IO can help you. The GitHub is I'm showing the GitHub repo here, which is github.com/TensorFlow/IO. That's the repo. We also have a nice documentation website, which is also part of TensorFlow org. We have lots of guide and tutorials, and each guide is a Google Colab, so you can just follow through those tutorials line by line and see how everything works. And the installation, finally, the installation of TensorFlow IO is very straightforward. Pip install TensorFlow-IO, that's all you need. As long as your local machine system can run TensorFlow, TensorFlow IO can equally run, because it's an extension that's built with the same environment. That's okay. That's pretty much the talk for today. Just wondering, anyone has any questions want to ask?
There is a question by Sandia. I hope I'm pronouncing the name correctly. Does it mean that the TensorFlow is automatically run in batch mode because input data is in batches? This is one question. Can you answer this? But also, Gunnar before asked for more clarification between eager mode and graph mode. So if you can answer those, and then there'll be more questions. I see many more are coming.
Okay. I think I'll try to explain the eager mode and graph mode. To do a comparison between TensorFlow and Python. In Python, you can do a interpreter mode, or you can run the Python program and compile the Python program as a binary, right? The graph mode roughly equals you compile the Python into a binary program. And the eager mode roughly equals to the interactive interpreter mode, such as you type a line and you get the result immediately. So the advantage, pros and cons of graph and eager mode is obvious. If you try to build up a model and try to do some debugging, you really want to see the result line by line to make sure there's nothing wrong. But when you try to run that in production, you want to do that in compiled graph mode because it can speed up. And the TensorFlow has many optimizations to make sure it's fully speed up in graph mode. Actually, I mean, I think some of you guys know PyTorch. I mean, there's no denial. PyTorch has a lot of momentum as well. PyTorch's strength was that it comes with the eager mode. So as you type a line, they give you a result immediately. In the past, the TensorFlow only have graph mode, which is a little bit awkward for people who want to do debugging. Because when you do debugging, you cannot just type lines, see what's happening. You have to essentially write your model in complete form. And then you dispatch to allow the model to run and give you the result. But if you try to see, okay, is there anything wrong in between in this line? I mean, it's very hard to debug. And that's no denial. That's one reason the PyTorch was popular for quite some time. But now TensorFlow has an eager mode as well. So if you run TensorFlow, by default it's eager mode. But if you run your as I showed in the slide, in tf.keras by default, if you already have a model built with a compiled model, your model will run in graph mode. I think that answers the graph mode versus eager mode question. Another question is how does the data feed into the graph to run continuously? As I mentioned, when in tf.keras, if you compile your model, tf.keras will actually compile the model and wire up a pipeline. As long as you have a as long as your input is data set, the tf.keras will just fetching the model in a poll way. It will continue to poll the data until it's running out. So in this way, it automatically handles the pipeline continuously. This gives you the opportunity to run that in speed mode. So that's why we talk about tf.data, because it's usually for pipeline usage. If you say I have a model, but I want to see step by step, a tf.data may not be the best way. But we are talking about production. In production, you want to fully utilize all your compute power, especially GPU power, because the GPU is very expensive nowadays. Yeah. Okay. I think that answers the question, right?
Yeah, there's two questions. There's one more question, and I have a question of my own, but let's start with those. Sherry said, she asked, when trying to Google Colab exercise you gave, will we run into the same kind of data pipeline bottleneck or no? Wondering if we need to be concerned. You gave some Google Colab things there.
Okay. As I explained, the pipeline, the core component to solve the pipeline issue is tf.data. As long as your data is feeding into tf.keras in the format of tf.data, the pipeline is automatically wired up. So you should get maximized throughput already, and that happens anywhere you run. If you run that in local machine, as long as you pass through tf.data, you get the maximum speed. If you run in Google Colab, you also get a max speed. If I show additional, let me see if I can show some of the tutorial. If you can see this. The tutorial is very detailed, so I think you definitely will have no trouble to follow through. The tutorial will explain to you, say, okay, you install TensorFlow IO here, and then you install and set up PostgreSQL, which even give you everything you need to get the data. And for demo purposes, we pre-populate the data, but the data is already available. So you can just dump the data from somewhere else into a PostgreSQL. And the next step is that we construct the data set. And that's very important. Once you construct the data set will not run until you pass to tf.keras. So as long as you construct data set, it's not going to read anything. It just sits there, ready to be used. But then if you pass the data set, let me see. You pass the data set to model.fit, the Keras will just automatically fetch the data in your data set pipeline and as much as possible, and you can maximize your throughput. Does that answer the question?
I guess so. Sherry will say yes or no. Don is asking a question. Have you tested TensorFlow IO with Kubeflow with some sort of SQL as your DB?
I mean, I certainly heard of Kubeflow. I think they are totally different things. Kubeflow is the focus of Kubeflow is more like trying to distribute workload into into a system such that you can have multiple nodes. I'm not sure Kubeflow is the best thing to input the data into TensorFlow, because we mentioned about the TensorFlow graph mode. In graph mode, TensorFlow will actually build up all the operations into graphs. So a graph consists of operations, and in tf.data or the whole data pipeline, the source node is actually part of graph. So if you say, okay, TensorFlow IO, what's the difference between TensorFlow IO and the Kubeflow? I think the thing is, with TensorFlow IO, your data processing is part of the TensorFlow graph. I think that's actually could be the key to speed up. For Kubeflow, I think the strength of Kubeflow is to distribute your workload into multiple node or even into a big cluster. I think they have different purpose.
Okay, I have one question, and please just give a quick answer.
Yeah.
I'm trying to get to Gunnar because he has an interesting presentation as well. My question is that if when you usually plug in data into a TensorFlow neural network, you have to handle a lot of stuff like encoding of characters and stuff like that. In short, does TensorFlow IO keep you away from doing all this and does this for you?
Okay. You still need to, like I said, you probably need to do something, because unless a format or unless not just the file format, also data format is known beforehand. Someone has to do something. For example, if your format is a string, you want to convert it to a, let's say, convert it to a floating point. There are APIs allow you to do the conversion, but unless you tell TensorFlow, say, okay, I want to convert from string to a floating point, I mean, it's very hard for a program to automatically do that for you, right?
Okay, so you still need to do some things. This is the answer.
Yes, but the APIs are there, so you can easily apply those APIs.
Okay, so it helps you do those things.
Yes.
That's the short answer. Thank you very much. I would like everyone to thank Yong Tang. Yong, stick around. Let's hear Gunnar. But everyone, please, you can unmute yourself. We'll make some echoes, and please.
Clap.
Thank you. I'm gonna hand over to Gunnar. They listen to him excellent presentation about cancer and medical stuff. I think that's more interesting.
Yeah, stick around. We have Gunnar now to tell us how he uses data, not only how he ingests it. And he's going to talk about cancer, but he does other things with his graph things, and he'll tell you more. So, Yang, if you, I see you no longer presenting. Gunnar, it's your turn to present, and everyone stick around. Even after Gunnar is finished, we can have and talk more. And by the way, we're getting record number of people watching in COVID times. We haven't seen those numbers yet. So, Gunnar.
Hey, thanks. Hey, Ken, I see you here. I haven't seen you in a long time. Fantastic. All right, let's see. I think I probably want to use this. And I usually present this as from the sort of the output and give the the sort of human side of the story. So my talk's going to be quite a bit different from Yong's excellent talk. Maybe a little bit less technical, but I hope to present a lot of pieces. Can you guys see my screen right now? You see me, okay.
You see you press the present button on Google.
Yeah, let me try again, okay.
Once you present it, it will take over, and we'll see you as a small thing on the side, and here we go.
Okay.
Okay, now we see your screen. Good.
Fantastic. All right, so I run a data science company out of Austin, and a lot of what I'm going to tell you is something sort of what I do and why I do it. The idea is that we want to take highly technical data sets and make them into accessible, usable things that everybody can use. the reason is that, we see data science, it's got a lot of uses for governments, for political campaigns, for, these big power players, but we don't see a lot of uses for just regular folks. And we believe that this should change, and we're looking into, tools, using tools in Python and other tools to sort of make stuff more available to folks. So one thing is a knowledge graph. Kraken is the type of knowledge graph we use. And that is one way to analyze data streams, or highly technical data streams. We'll talk about how to build that out and how to utilize that for cancer data. So the title of the talk is digging into public cancer literature using Python. As you guys all should know, we have an extremely rich and very expensive data set in PubMed that's available to everybody, and it's been paid for by everybody, so we should all leverage it. It's along the magnitude of maybe 26 million papers that are, all very expensive in terms of human costs and in terms of actual dollars. So let's see. The things that that sort of keep us away from our data, right? Our data streams are data management, collecting, cleaning, and organizing. Data analysis, how do you derive information from these data sets? And then, and how do you get that, these very rich data sets that are coming to the forefront, how do you bring them to the forefront and allow people to use them? One tool is the knowledge graph, which is a graph that we can use to slip in entities, which would be papers and cancer outcomes and genes, all sorts of entities, and connect them together and ask questions. I mean, everybody's familiar with the front end of this, like Google is going to use a knowledge graph on its back end to give you information. But what I want to do is start building out those things, and show people how to build those for themselves. We've built 4 main data stories in the company so far. There's BioPredictor, which is how I met Jacob when I was talking at AnacondaCon. So basically the idea was we have biotech domain companies coming up, and there's many different types. They're very complicated. Most people don't know what they really are doing, and there are experts who may, read a lot and figure out which ones are going to be successful and which ones aren't, but maybe we should all be involved in this discussion. Collaborations comes from collaboration and patent data, so we can actually, we pulled PubMed data and patent data into a graph, and you can see who talks to who collaborates with who, and we can pull out knowledge communities and information communities that way. What I'll talk to you about today is the cancer graph. Coming from some of the same data sources, we can pull out cancer data, and I'll tell you why this might become important. I guess you can probably imagine for any individual, right? So I've made this pancreatic cancer subgraph. But I also built in the ability to make any type of graph that you want from PubMed data. So it basically works on a search term. So I think that's a big lever for this. So it's not only cancer, it's all PubMed. And then there's cocktails. There's a newer graph that we're doing. One of our data scientists she was going to be a bartender. She's very interested in flavors. So she's been building out the cocktail graph, and there's actually a scientific drill down. We can get into ingredients and effects of ingredients in cocktails, or the flavor profile science, right? So I told you that I was going to give you the broad overview and sort of motivate it that way. But I will get to the Python. So this is the one graph I'll talk to you about. This is the cancer graph. Let's see. The reason why this is important is, I know you guys are all technical people, but you may have had this experience where you've maybe, for me, I've gone to graduate school. I did a PhD in genomics and a postdoc in genomics, so I should be very familiar with this information. But when my sister got sick with pancreatic cancer, I said, well, I really should be able to help her, but the best she could do was go to the people around her and ask what they did when they got sick with cancer, right? So I couldn't actually spin up a report. I couldn't actually get to any good information. And a lot of the stuff she was working with was sort of rumor level stuff from people who may not have any training at all. And that to me is there's a big problem there, because at this point we have access to all these things, right? And I have all the skills to analyze these. So what could you do? And again, this is just sort of the values of the company that I run. The idea is that there's maybe in a pharma company, somebody would have access to this information, but why shouldn't we all have access to this information, right? So let's see, looking at the literature. Okay, so let's just dive in and read. Now, I've heard people talk about this. They said, well, you know, I was the most educated in my family. When somebody in my family got sick, they said, read the literature and figure out how to fix me, right? That's not really a good method, right? If you look at pancreatic cancer, there's 105,000 highly technical references. Sure, you can spend weeks and weeks reading this, but your doctor probably already has. They probably already have an opinion. And maybe there's a question that, you know, that your relative or you might have that, you know, they don't have an answer to. So how do we bridge that gap, right? I asked her, you know, what's the problem? And she said, you know, chemo is really hard. Actually, that's one of the biggest things with pancreatic cancer. You can sort of knock it down, but when you get more and more aggressive treatments, it just becomes harder and harder. And people you end up choosing to die rather than keep on doing those treatment. So I thought maybe a chemotherapy side effect graph would be useful, right? Maybe pull out that stuff. Let's see. And then she said, you know, who can I contact about new cutting edge treatments? I think this is probably a pretty common request, like who's doing the best work, right? What are the hot spots in the country? And this is another thing that we can get, and it's all available. It's just the I told my students, even if you're a polymath, you're probably going to run out of energy. You're probably not going to be able to understand all this stuff. And what I'm going to show you now, I think, is actually going to allow people to, you know, to leverage their brain at a higher level, right? So, okay, so this is the basic knowledge graph. It employs these different pieces. Kraken AI is the database. It's a knowledge graph database. So it's a graph structure, but it's got a lot more richer encoding. It's not your old semantic graph. And the data set is the NCBI, which is PubMed, right? So there's 26 million rich data points, which are papers, right, that can be parsed into items and entities. And then there's BioPython. And BioPython can query this data set, and it can take out slices, and it can do a lot of things. So I think the Python part is mostly BioPython. And then the connector between this data and then Kraken AI, right? And then finally, there's a query system, which we can query and get actual information out. The things that I thought were interesting in this data set were the keywords. So every paper has keywords associated with it. Abstract text, right? The PI has been responsible for distilling down their results into a small paragraph, so the abstract should be in there. The title is not listed here, but that's, you know, their biggest claim about what they did, right? So that's a huge deal. That probably should be here. And then there's authors. That includes affiliations, hospitals. So if you want to figure out the hotspots for this type of thing, and then chemicals. So chemicals, I thought, would be really important for like side effects and treatment regimes. Okay, so how do you build the pipeline? So the rest of the talk, I'm gonna just talk to you about how I built out this pipeline, and then give an example of how to use it, and then tell you sort of where this is going, and give you some other resources if you want to build out a similar pipeline or use this pipeline or whatnot. So on a Mac, it's very convenient. You can use brew. So just brew tap Kraken Labs, brew install Kraken Labs, the core, and then upgrade. So you can do that, and you've got the server running on your system. Let's see. It's a little more complicated on Linux, but all systems can build this out and serve this. Let's see. Okay. And then we can just step back and think about what exactly we'll be loading into this data set. Kraken has three main types of things: entities, different types of objects, relations, and attributes. So the attributes can belong to the entities. So an entity can have different attributes. A relation can relate different entities to each other. Each of these has its own ability to specify behaviors. Like, so there's a keyword has, and that'll specify an attribute type. So a person has a name, right? For example, there's a plays and a relates. So these are the two things. So when you specify the way entities relate to each other, you can use the plays keyword, and you can use the relates keyword, and that'll restrict your schema so that it's not an open schema. And you can do things like forbid a person from marrying a building if you want to, right? You can actually enforce some set of logic onto your schema. So this is the core of Kraken, and then there's rules, and the rules are just logical statements that happen at query time, and you can actually infer things. Like if there's two individuals that have the same parents, but they're not considered siblings, you can use a rule to make them siblings, right? That's the type of thing. Questions on this stuff before I move to the next step? Yeah.
If someone wants to ask now. It goes only more complicated. I have a question to heat things up. Can you say, you mentioned centralized data, like, PubMed is like, well, in one place, you can download it all and use it. Like, Wikipedia data you could probably handle as well. But is there like, can you do this with decentralized data, or you have to centralize it before? Does it have to be formatted the same way?
Yeah, I mean, actually, even with the PubMed data, there's quite a big parsing effort, right? So, I mean, you could certainly use decentralized data and just stream it in, right? So as you get different data points, you could just add them in if you can classify them as an entity, but you're gonna have to write your wrappers, right? That stuff is not written. It's only the schema and then those different objects. That's the thing that's enforced in Kraken. So there's a lot of overhead that you have to write to make it, to pull everything in and make it all fit together. That's one thing about this database is I guess I'm not sure if it's unique to Kraken, but there's certainly a lot of overhead, like enforcing structure.
Can you use Kraken to actually figure out structure and then decide what you want, like kind of filter things out of something that is unstructured?
Yeah. So I mean, there's the KGCN layer. So there's actually a CNN layer that will go through, and if you have a sparsely labeled graph, like the example they use in the presentations are endangered species, right? Let's say you have all species in a graph, and you know that some of them are endangered because maybe they're used for pocketbooks and meat. You can actually have the CNN go through and find those examples and then predict when there's another endangered animal or another animal that's likely to be endangered based on its characteristics, like it has the attributes that's used for pocketbooks and meat. So those are the examples that we see. So yes, there's it's kind of a neat system where you've got a graph, and then you can have a graph on top of that produces embeddings. It's like sort of a summary graph, right? So yeah.
Yeah, someone is asking, Michael is asking if there's a CNN baked into the data set.
It's a second package. It's part of the Kraken tool set. It doesn't come in on the main Kraken thing, but you can even run it from a separate computer. So it's like a client system, and then the KGCNN runs on top of that. So it queries the graph and builds and then loads it into Kraken. So yeah, it's a client system. Yeah.
I had a question, Gunnar. So the knowledge graph that you're building, is it hosted somewhere, or have you thought about like hosting this graph like in other public repos, like data repos, like data.world, for example?
Yeah, I mean, we've got our servers here. We host them on AWS and then on my local servers. And we've thought a lot about how we want to, provide access to these. But yeah, we haven't. I'd like to talk to you about if you have experience hosting stuff, because we're data scientists. We don't have a lot of experience on like deploying things. It's just a lot of analytics. So
Prashant, are you from data.world?
No, I'm not. I'm not marketing them, but yeah, I mean, I think I've looked at data.world, and the advantage of hosting it over there is you can then work with other related data sets and enrich your graph, right? And so I feel like, and then of course it's an ecosystem. Like there are users who can work on your graph, and yeah. It's like they call it the GitHub of data. So.
Gunnar, I'll introduce you to some people from data.world another time. For now, let's continue with the presentation unless someone else has something related. I think Michael is asking, so BioPython is used for text processing?
BioPython it's a big ecosystem that interfaces with like biological objects, biological data sets. I guess text processing, not so much. It's more, I think it's more for harvesting data sets.
Okay,
At least
so
that's how I use it.
interfacing with PubMed is like baked into Python. Is that what I'm getting? Okay.
Yeah, and it's pretty big. I think it probably does Uniprot, ClinVar, like all the huge data sets, you know? The idea is it's a one-stop shop for biological data. If you want to get nucleotides, genomes, all that stuff. So I guess you could say it's data processing because you know it's gonna help you manage those long strings of nucleotides called genes, anything that's like biology, right? Cool. Okay, so let's see. So the first step is the schema, and then I'll just give you some examples of pieces of what's required. This is just an example of PubMed Grackle schema. So you define the schema. You define abstract text. So these are all attributes. You define your attributes, right? So it's abstract text, author name. If it is a PubMed article, author affiliation, PubMed ID, text, and title, right? And these are all strings. So that's just attributes. We would define our entities, right? So these are all different entities. We've got a PubMed article entity here, and it's got the key PubMed ID. So this enforces that there's only one of them, right? It's like a foreign key that's the single key, and then it has title, has abstract, pub date. It's got all these different attributes. These are the roles that it plays. It plays author container. So a PubMed article can hold an author. It can hold a keyword. It can hold a publication. Meaning, I think this would mean like a journal publication. Yeah, that would make sense. And then author subentity and keyword subentity. So you notice that these are all, there's an inheritance scheme, right? So these are all subentities. And then keyword plays contained keyword. So you can see the play word here and also here, right? So these two things are bound together in a relation. And we'll see that in the next slide. So you have to specify the relationships. So we call this pub contains author, and we've got the relates stated here. Relates author to container, relates contained to author. And similarly, the keyword relates keyword to container and contained to keyword. So those are the three different types of entities and how you specify them.
So the system itself, like it looks for those entities as if it is structured in a table, or it extracts them from text. That's like the author, does it know that's the author because the word author comes before or something, or does it realizes it itself somehow?
I have to write all the code to do that. So I do insert statements. They look kind of like SQL insert statements. So I'll load an author in, and I'll say this is an author, and then it'll load that author in, and it'll check for like duplications and stuff.
Okay.
It do extract it automatically. Although we could write wrappers to do that, right?
Okay, thank you.
Yeah, there's actually an Israeli group called that we just worked for called Clear Sky, and well, actually it wasn't Clear Sky, it was OpenCTI. They wrote a wrapper for Kraken, and that wrapper you throw papers in, and it takes out what they call observations. It breaks the paper into pieces and then does what you said. It loads everything into different pieces into Kraken, which is kind of cool. So if you guys are really interested in that, that's a pretty mature system that was put together by ANSI. That's a really nice way to wrap this and have a lot of the work done for you. So, so let's see. Connect to Kraken. Okay, so you connect to Kraken. This is just what you do on your command line. You start your server, you check the status, you build a key space, and you load your schema, right? So you do all of that, and then you're ready to go with that schema inside the database, and then we're ready to load data. The next step would be to check it. So you can yeah.
Tom is asking, can you exactly tell us? I think all of the questions made things a little bit unclear. Can you say exactly, restate your objective, what you're trying to do?
Oh, what I'm trying to do?
Yeah.
So my goal with this graph was to organize PubMed data so that my sister, who had pancreatic cancer, could get answers and get reliable data sources together in a human readable form, right? So she could ask a question, and I'll show you an example question at the end.
Okay.
That she asked me. Yeah.
Good. This answers Tom.
Yeah. So you can look at all the different things, and you can see all the things, and make show that the actual schema has been loaded. Let's see. And then we get to the actual loading step. This is, I think, what Jacob was asking about. You've got to have these data structures. It takes in CSVs. You can also load it in JSON, but I loaded this one in CSVs. So basically what I've done is I've made a logging system, or I've turned on logging, and I've made a tree of folders where I can put in all my input data right after I parse it. The next step would be to get the data from Entrez, right? So this is over here is a pretty easy way to get PubMed data, entrez.esearch. It's got a lot of the e-tools, eSearch and eFetch I'll cover, but there's a bunch more. And this is BioGraphen, right? So I can say, I want to go into the PubMed database. This is my email, return 5 items at a time, or whatever, and sort by relevance, and input a query, right? So this is the function, and my query is going to be a string query. It's going to look through the PubMed data sets and pull back stuff that hits that query. So we can do that. So what we've done is we've got these PubMed IDs. So basically what I did was I specified pancreatic cancer side effects. I think that's on the next slide. And then I ran my query, and then I partitioned it into this list of lists. So I've got 5 at a time. And like Yong was saying, we just process it in batch because otherwise it'll choke. So I'm doing 5 of these PubMed papers at a time. Let's see. And then I can run the actual code right here. So what this is it's got a connection to my Kraken instance. It's running on localhost. This is the standard place it runs, 4855. And it's got a key space already, PubMed ref cancer. And then I will go through my partition list and 5 at a time. I'll fetch details. I have to talk to Entrez again. So I've got the PubMed IDs, but I want the specific features. I don't want the whole blob of data. So I use fetch details to get the the fields I want, and then I load them into Kraken, right? And I just have to specify my key space and my URI to do that. So this is what fetch details looks like. It's actually very similar. It's just got the eFetch method, which is it's a lot more specific, right? So I can specify a smaller set of things. So, all right. And this is what the data looks like. It's just a piece of the data, but you can see we're getting what we think we're getting. These are article titles, right? Nursing implications of chemotherapy agents, right? Enzyme treated, okay. Maybe, oh wait, this is actually it, right? So enzyme treated extract downregulates heat shock protein 27 in pancreatic cancer cells, okay? So it looks like we're getting what we want. We've got references. We've got other fields too. Title, abstract keywords, mesh terms, which is a type of keyword in a structure, citation information, journal, PubMed ID, and chemicals, which is important, right? We want to find out the suite of chemicals that are used in each of these papers. Okay, so I was struggling whether I should show you this. This is just parsing code, right? So I do have to parse this from my CSV files. Right now I've got these things in CSV format, and we've got to parse them into a format that can allow us to insert into the database. Actually, I said that wrong. This is before that. This is actually parsing this thing into CSVs. So it's taking this structure and splitting it up into like an author table that has author and affiliate, abstract table that has abstract and reference, however I want to insert it. So you can see just in a simple example here, author name, author affiliation. Again, you've got cancer researchers and we've got their locations. This is kind of interesting, Department of Geography and Anthropology. Or I would guess that this is probably a pancreatic cancer paper, but it would be interesting to look at. And then you can see all the different CSV tables that I've parsed to load this in. And they're all this very simple pairwise format or whatnot. Let's see. And then it has this structure where, or I wrote the structure where you've got to tell it where the file is, and then write an article, a template that's going to do the insertion, right? Because we don't want to have to write this over and over again. And I've got this list of pairs of locations and insertion templates. Questions? And I'm marching through this pretty quick.
No, you actually, so you're extracting information from a specific path. Can it be an XML file? Like you say those are the XML tags I'm looking at?
These at this point are CSV files. This is written to parse CSV files, but you could parse XML if you write an XML parser.
Okay, so this is already parsing the CSV that you showed that already was constructed.
Yeah, the CSV is already constructed, so I just use an insert statement and a CSV file at this point. It's very simple right now.
Okay, sorry,
yeah.
I didn't get it. Thank you.
Yeah, and you would write this differently if you wanted to parse XML files, probably. I don't think you want to insert XML directly using the Kraken insert statement.
I misunderstood. Thank you for the clarification.
Yeah.
Go on, please.
Cool. So just this is what the insert statement looks like. This is another language like Sparkle or SQL. It's called Grackle. And it's got the basic structure here is it's got a variable. So you've got your variable P as a person, and it's got these properties, right? So person has a name. The name is Bob, right? Person has a phone number, and the phone number is captured right here. So this is the language that you use to make the insert statements. Here you can see the example of one of these insert statements. It's inserting a relation. So it's, I'll go back to it. Match PubMed article is a PubMed article, has PubMed ID. And then this comes in from the data set. There's the PubMed ID that comes in from the data set. And then we just append it. So you can see the append, the sequential append. Author is an author, has author name, and we stick the author name in here. And then insert author container. So this is a key value pair. So we've got author container and PubMed article, contained author, and the actual author. So you can see that this is the relationship right here. And the name of the relationship is pub contained author, right? So that's kind of the structure. You can imagine when it goes in, it's only one, it's a 3-line string, right? So the whole thing gets concatenated. It doesn't do this sequentially. It's concatenating these things together as one query statement. Little complicated, so I'll just leave that there for a second.
So is the graph database reading these CSVs directly and applying these like insert statements in bulk, or is that part of your ETL script?
Yeah, the ETL script is grabbing this. This is my Python wrap, my template, right? So this is a function that I'm calling a template, and the function is ingesting the CSV and parsing the CSV, and then this thing makes the Grackle query. So the insert query has to be written like a SQL query, right? It's just like one string, which is composed by this and populated, in these fields. So that's the Grackle doesn't care about this. This is all Python, right?
Oh, okay.
Yeah, it's what it wants is what this thing returns. Sorry if this is like there's a lot of code here. This is similar. It's maybe a little bit more straightforward because it's just building an entity, right, instead of the relationship. Again, it takes the author CSV, right? So it's that template. It sucks in the author CSV. It takes the author name, it takes the author affiliation, and then it appends a semicolon to the end of it. So again, this is a query string. It turns into a query string that comes out of this function. Then this is the actual communication with Kraken. The way we do this is we take the input. So that's that input, the list of paired templates and data sets, key space and a URI. It opens the client, right, with this URI as client, and then takes that client and initiates a session with a key space. So it's sort of strung together in this, and all packed into this object session, right? So this object session is the thing we use to talk to Kraken, right? So once we do these two steps, we're able to go through the inputs and load them into that session. So that's the connection to Kraken. And this is just an update statement. And the actual loading looks like this. Here's really the, if we want to get down to the brass tacks and get to the meat of it, it's this, right? This is the thing that talks to Kraken. So all that was staging this, 10-line insertion into a session. So we've got a session, we make a transaction, we tell it to write, right? Once we have that write action, we store that as transaction, and we take the insert query and we put it into that session. Let's see, right here, right? So transaction.query, insert query. There's the whole thing, right? This is what we're doing. We built this and we're sticking it into the database and then committing it, right? So I guess these two lines really summarize what's actually happening at the end. All right. Now, what do you do with all this, right? So we've built our schema, we've built our key space, we've loaded our key space with data from BioKraken, right? So we've got actual paper data. I want to emphasize that we can do this over and over again now with any keywords, right? So it's already written. You can just use whatever keywords you want. And then we can use this tool, or we can use a Kraken client. Actually, a Kraken client might be a better way to do it if you're doing this stuff in bulk. But if you're just exploring, Kraken Workbase is a really good way to go. So we can just specify localhost 4855, and this browser will let us explore the graph space. So just to remind you, we'll be querying using Grackle. So $P is a person, has the name Bob, has a phone number, and we load the phone number into this variable that we can query. So that's the basic Grackle anatomy. So we wanted to ask a meaningful question. So the meaningful question is like, maybe if we're interested in side effects for cancer, what are the most important treatments? What are people doing, right? Which chemicals are connected to each other? So other cocktails, right? Do they exist? Can we get this out of the graph? And then which chemicals clusters, who's having the most success, that kind of stuff. So we want to really look at the chemical, the research group and chemical overlap, I think is the question that I went after. Yeah, this is it. Are there groups of papers that center around ideas or sets of chemicals? Which are the most relevant for chemosymptom mediation? That's sort of what I was going after. So I'll just show you what that looks like. We can ask the graph any question we want that has to do with the entities that are loaded. And then this is the query that I came up with for an example. Match P is a PubMed article, right? So we load the PubMed article into variable P. It has a title T. It has a PubMed ID. And we capture all those things. Next step, chemical is a chemical. It has a chemical name. Okay, next step. Now we want to bind those two things together, right? So here's the relationship step. Chemical contained is, and then you've got key value pairs. Contained chemical is the chemical. Contained container is the PubMed article. So, and that's a PubMed contained chemical. So just to summarize, what I'm really after is a paper that has a chemical in it, right? I want to bind the paper to its chemicals, and then I want to ask which titles have a side effect, and in the last part, I get PubMed ID, and chemical contained, right? So I want to find the chemicals that are in each paper. Just basically what I said before. Show us the chemicals mentioned in each paper, and this is the query string that gets us that. It's more specific because I said title contains side effect, because I don't want 305 papers. I don't want all the chemicals in 305 papers. I want the things that are highly constrained for side effects, right? So what I got back was this, and you can see there's 1, 2, 3, 4, 5, 6 papers, and it looks like 3 of them are clustering around one cocktail or one group of chemicals, and then there's some other chemicals there, and then some of them have different chemicals. And that's as far as I got, but I hope you can understand how this would be useful in exploring this type of data. Now, the question that emerges next is, where do you go with this? What do you do with this? Okay, so maybe you understand that there's a cocktail that's used a lot, and then some stuff that's not. Now this is very sparse. Remember, I only sliced out 500 papers from the 100,000. We could do this with more, but it would be a lot more overhead. But so I just do this sort of to show you what's possible. This is the schema that I built up. You can see the PubMed article, keyword, chemical, journal, mesh, term, and author with all their attributes here and all the relationships here. But what I want to tell you is that really where we want to go is here. This is something that Graken built up. It's for COVID-19, but it's BioGraken. So we can look at it a little bit closer. These over here are all the research entities, things like research groups, university, individual researchers, right? And whatnot. This is actually named. So everything has a name. So everything's bound to name. So we can look a little closer. You can see organization, laboratory, company, institution. Let's see, we can look at this section over here. That's patent. And then these are all like journal articles and stuff. Patents, journal articles, anything written. NERs, there's NERs in here, which are named elements. Paragraph, sentences, all that stuff. And you can look at patents. We can just look title, volume. So all the thing about written stuff is here. And then over here are all the biological entities. This is protein. It's very closely linked to gene. I couldn't even select one and not the other. And then there's chemical, right? So that's this. So we can look at this closely. Gene, chemical, protein. So all these other elements are here. So I guess I just want to say that looks like a hairball, but we can start to tease it out as well. And we can approach this problem of overwhelming deep tech information in a systematic way. So that's my whole thing. And I just want to thank our group. So this is my group over here. We got a lot of excellent, really intelligent people, all working on this direction, this graph analysis, and sort of leveling, democratizing data through graph analysis and math, right? Okay. Any questions?
I have many, but let's see what other questions are.
I have a question, Gunnar. How has your sister responded to this data? Is she geeking out about it, or how has she explored, and how has it helped her?
She unfortunately passed. I talked about this in February, and she's passed since then. I don't think the problem of understanding medical data is not gone, right? But and I still think that is a cue. But unfortunately, yeah, she didn't. She actually stopped taking chemotherapy. She was doing very well, but she couldn't handle the side effects. It was exactly what she said. Within a week, she was just not doing well. So, yeah.
What you said is that the problem of understanding medical data does not go away. It's an understatement. It only becomes worse. I'm not kidding. It's like I work with medical data, and I'm telling you, it becomes worse and worse and worse the more data we have. We need tools like you're talking about. But let's see, more questions.
I've got a few questions. The first is deep tech. Is that just a shorthand for like deep technical information?
I think it's kind of contentious. I'm probably using it a little bit loosely. So deep tech would be anything that requires a large amount of training to actually utilize, right, and understand. At least that's the way I'm using it. Yeah, so that's what I mean by that. I think there is a lot of information like that, and maybe I'm sort of misusing it. I don't know. Maybe.
Okay.
But that's what I mean. I mean something that requires a PhD to understand.
All right. That's what I thought you meant it as. And then with Graken, so if you were to like attempt this with a more like a classic relational, like a RDBMS or like a Postgres or something, where does Graken, aside from like the graph visualizations, like what makes it better suited for this kind of like storing this specific kind of data than a more traditional system?
Well, I think you need to be a lot more explicit with a more traditional system. You can certainly model these things in a more traditional system, but you need to specify your tables first of all, right?
Yeah.
This actually, you can add an entity on the fly, right? So if something happens that makes a new entity and has relationships to things that are already there, you can add it on the fly. So that I think that's the thing. And then the other thing is that you can predict relationships that aren't there. So it allows you to do, at query time to actually predict relationships that were never specified.
Wow.
And then there's the other thing, which is really cool, and it's still being built out as that KGCNN stuff. So you can actually take this graph and you can layer something that's a summary graph on top of it, and another summary graph on top of it, which they're essentially just summary embeddings, right? So like a whole cluster might represent an endangered species, right? And that might be just one node on the upper layer. So all that stuff, I think, probably could be engineered with SQL, but I don't think it's as easy.
Yeah, I think. Yeah, I'll just like to add. I think with relational, sometimes it's hard to go beyond like one levels, right? Like for example, you can, if you have a table, like for example, if you want to get the manager of an employee, yes, you could have that one single table, but then how about you get like 5 levels of managers, right? And so if you model it as a graph where you have identities or employees and they are connected via like a manager relationship, then you can get that tree pretty easily using a graph query.
So let me look at the chat. So deep tech and deep learning, very different, right? Deep tech would be just the amount of information, the amount of expertise you need to analyze the data, to understand the data, and then deep learning would be like TensorFlow, right, where you're actually applying a neural net to a data set. So those are different. Is there a fundamental difference between what one can do in research and what one can engage for medical treatment? Have you found a strategy to use it? So Mike, what do you mean? Are you Mike?
No, it's Matthew. Yeah. So for example, you can find research papers that can cure cancer in mice, but those same processes won't cure people in a hospital setting. And then even if it could be proved that it could happen, you still have to go through clinical trials, FDA clearance. And so did you find a way to easily sort between those different data sources?
That's a really hard question. I mean, I think with COVID, we're understanding how difficult finding a biological solution could be, right? I mean, we've got vaccines for other stuff, but finding a COVID vaccine is even very challenging, right? So I don't know. I mean, that's a really interesting question in terms of like, are you thinking about like prospecting the data and maybe trying to figure out what's most promising?
Yeah, I've worked up and down as a scientist in the treatment chain, either as a medical physicist or at the FDA itself. So I'm curious to see what people have gotten to in their careers so far.
Yeah. I mean, I would imagine that. I don't know. I kind of want to layer a collaboration graph on top of the biological data, right? I mean, like that Theanos thing, right? With the with all those crazy claims. I think anybody who was in biology could understand that there was that there's not a lot of backup for that. But I think maybe if you figure out who's who and who they know and who they're interacting with, maybe that would be a good way to figure out, where the smart money is. I guess that's what I would think.
Okay, thanks.
Sherry asked something. What type of info you prefer to include in your schema?
Well, I really like the individual information, like what people say they're doing, like titles, and also who people are and who they know. I think that I like that quite a bit. In terms of like bench work and stuff, that's also really interesting. Like, what are the genes? And I spent a lot of time doing genomics, and it seems like if you're looking at specific genes and biological elements, there's a high burden of proof, right? Like if you say, okay, well there's a gene that's involved in that's connected to COVID, right? And that gene seems to interact with the coat. You know, in this number of papers, you've got to go ahead and test it at the bench. So what I'd like to do is sort of look at clusters of ideas and see who's backing them up instead of looking at actual biological entities and making predictions about what those things are. But I mean, there's certainly the other side, right? You could definitely include biological entities as well. But if you're asking what I prefer thinking about who's been successful in the past and who they know and what they're talking about.
Tom is asking, I might have missed, but is there an NLP component to this?
The simple graph I showed you didn't have an NLP component. This COVID graph has an NLP component. There's a named entity recognition layer, so these are NERs, and those named entity recognition layers items are mapped into this, and they break up any abstract or any paper that's in here. Named element recognition, I think named entity recognition. But anyway, it'll call out if something is a gene, if something is whatever it might be, a species. There's a whole ontology that's mapped on top of each item. So that's in this COVID graph.
Unless someone else has questions, I have a few. So specifically for the COVID graph, you collecting the data only from PubMed?
No, this is from Uniprot. This is not my work. This is Kraken, right here. You guys see that?
It shows underneath your slider thingy. You have to move the slide because it doesn't show the.
Yeah. Okay, let's see. Can I don't want to exit this. Let's see.
Yeah, this should be better maybe. Or drag it up or down. Or just if you just copy it and put it in the chat.
Okay. This is it. Right? So this is the easy way to do this. There. Cord 19. So this is the course of peer-reviewed publications from bioRxiv about COVID. Cord NER, this is the NER data set. To recognize the named element entity named entities. It's got Uniprot in it. It's got coronavirus data. It's got the drug gene interaction data set. It's human protein atlas. Reactome, so it's got interactions between different biological entities. And then DisGeneNet, so it's got curated disease associations. Okay. So it's got all that in there.
It's multiple databases, this is what you're showing me, and it connects multiple databases and shows you connections between those.
Yes, exactly.
Okay, this is in short what I was asking. Okay, this is a lot of potential even now.
Yeah.
We should talk later, by the way. Here, Sherry is asking, well, Sherry, this is what I just asked. Yeah, the COVID data is from those sources that he showed. How do you deal with data that is non-standardized, like NLP, or do you have some other techniques?
So most of this stuff is standardized. Thankfully, there's a lot of money that goes into making biological data standardized. Let me see if I've dealt with any data that's not standardized. I usually use, whenever I can, I use convenient data sets because I want to get to the actual answer.
That's the problem everyone has, and this is why everyone focuses on those. I'm asking a bit beyond, because you do have capabilities of making all sorts of maybe intuitive connections by graph. The question is, how do you recognize them? This is where I'm missing the point.
So I guess I want to know, when you say non-standardized data sets, do you mean data sets that are from experiments, data sets from the wild, or something different than that?
Non-standardized meaning there is no standard that binds them.
I see. So maybe they have different new types of entities, and they don't. overlap?
The
Or?
entities are defined differently. Let's say you pull out an article from PubMed and then you take up some data from some other website, and is there any way that you can help there?
I mean, the only thing I can think of is to do just to do NLP and recognize common phrases and like, you know, combinations of words, right?
Okay. That's a start. But that is one of the biggest problems today in healthcare. The data is highly non-standardized to the point of pain. And
yeah.
And you do the simple solution I also take many times, which say, okay, go to the things that people standardize, which is a lot of hard work. Anyway, Ken is asking, Gunnar, okay, Gunnar is not asking, he's saying enjoy your talk very much.
Oh, fantastic.
Okay, and he left some contact information. Check out the chat. Okay, unless anyone has more questions, we can wrap up the video recording and post it later online to YouTube. That is, unless someone doesn't have any more questions. And by the way, you can go back and ask questions for the first talk as well. If some of the ideas came to you, for example, I'm curious if you can combine both talks. Like, some things can be done with TensorFlow, with TensorFlow IO, that can make things easier for Gunnar's kind of Gunnar's work. But this is my own ideas. But ask your questions away. And Sherry has a question.
So yeah, the COVID are just by reputation, by who put them together, right? Peer-reviewed data sets, right? So, well, I don't know. I'm looking at the COVID data set right now. You guys can see my screen, I think.
Yeah.
Yeah, I mean, this would be just by reputation, just grabbing what's got good reputation. But like, I mean, anything that's been produced by a good lab is most likely going to have some basis to it, I would imagine. I mean, these are actual publications. Not all of them peer-reviewed. You know, you saw that bioRxiv is one of the sources, and you can't really expect stuff to be peer-reviewed this fast. But yeah, I think again that goes back to like reputation and who did it, what the track record is. I think that's really important. Not to beat a dead horse. I think that's really crucially important.
Ross, I'm not sure if he's asking or stating. Seems like some examples of non-standardized dataset might be any sort of VCF or data from variety of omics data. Okay, I'm not sure. Is the question?
So it's kind of a follow-up to your question, Jacob. I don't know really that there's like a great response. I was just kind of giving like examples of where you might find like non-standardized data sets. Like, so VCF, you can specify like a ton of super custom headers, and like if you open a VCF file, you essentially have no clue what's in it unless you read these headers files in a very specific way. And then I saw, Gunnar, that you were also looking at like different kind of omics data. So you're looking at like proteomics versus like standard like NGS like genomics versus like RNA, and like I know that relating those things is not easy. Yeah.
I mean, so I guess the VCF example, if the data dictionary is very different, right, and the data is dirty, this would be, you know, it'd be interesting if you could write a wrapper that would stuff that stuff into different formats. I mean, the VCF would have sequences in it, right? So maybe you could parse out known genes or something like this and pull that stuff out. And then omics, all sorts of omics data. I mean, I guess there is a limited subset, right? Like, we aren't talking about a totally unstructured domain, right? We have proteins, right? Proteomics, and we have some maybe, you know, mass spec data for that. Maybe you have some metabolites. I mean, sure, there's a lot of stuff, but it is a finite universe.
It is, but you know, if you're, for example, joining like DNA and RNA data, you have to worry about all of the varieties of, you know, all the potential transcripts. So only joining like one data set to the other is ludicrous.
Yeah.
And that's like for one sample.
Yeah, you're making me very uncomfortable.
I'm asking this specifically because this is what I'm doing. So I want to know if you have a solution for me.
Yeah, no, I mean, and transcript stuff, right? Like, you look at the different stacks, the stacks of all varieties of transcript, right? So what's the actual gene, right? This is very difficult to know sometimes.
Yeah, fair enough.
William, I think, is suggesting looking at analyzing the number of citations and then figure out the better metric.
Oh, that was just a randomly thinking out loud kind of comment. I come from a humanities background, so that's the kind of crap that we need to do to quantify reliability. But
yeah, so William, I think this actually gets at a really good question. Like, is there a different metric of success, right? So there's the number of citations, maybe the number of citations that your friends have, right? Number of self citations. We could get really interesting and try, look at quality of researcher, right? Based on, well, I believe it goes back to, like, where are the good ideas, right? So how many good ideas float around in communities, right? Which, are you in a really good community? Are you a key player? I mean, I guess sort of like you could sort of think about like PageRank, where we jump from page to page randomly and try and figure out how many good links there are between different entities. I guess that's kind of something I like to think about.
Okay. Unless there are any more questions, we can stop the recording, but do stick around because we usually have the most interesting discussions off the record. So, any more questions by anyone, or can we stop the recording?
Hey, Jacob. Hi. I was curious on the answer provided for Tom's question. Like, I think for the first talk, I don't know if he got the answer. This was, I think, his question was around if it's easier to create batches for I think tf.data for images, but I think what happens when you have dependencies, I believe, and so where it is harder to create batches. So I was interested actually in the data sets that he was thinking about, where it's harder to do some of these batches.
So we need Yong to step in and answer those. Or maybe Tom wants to explain more about the question. I'm not sure.
Okay, so, sorry, maybe you want to elaborate the question a little bit more, because I mean, I didn't follow exactly the question.
I think Tom is on the call, so maybe he can. My understanding was, I think the examples that he was thinking about are, I think the data sets especially, I think it is challenging to create batches out of those in those data sets to use like for training, and so yeah, I'll just stop there and let Tom speak, I guess.
Tom, you can elaborate? Okay.
Just a second. Well, there is some obvious aspect of things like images, because they are localized. You know that data points, each data point connects to some immediate neighborhood and so forth. Whereas in general case, when you're trying to study something and find relationship, locality of interaction is not given. So how do you devise a batch in a situation like this?
Locality, you mean locality of image, or locality with respect to a series of batch of images?
Now you have a data about something, and how do you know that, what's the proximity, what's the sphere of influence of given piece of data? How do you know that you can stick it in a different batch and process it independently from some other batch that can be influenced by this? It's as simple.
I think I understand his question. Yong, if I understand it correctly, and you do correct me, Tom, he asks about, think about you take each batch, and each batch is like one is only cats, one is only dogs, one is only giraffes. And now when you train the system, he wants to know whether when you do this in batches, how do you make sure that it's like the training will be good? Am I correct, Tom?
Oh, is that the question? Okay.
He's nodding his head. I'm not sure if I understood him. Well, answer your best question.
Okay. So that's the batch we discussed here. It's a different concept. The batch essentially is just a way to batch up the data in a way such that we can do processing in parallel for a collection of images at the same time. Like remember at one point, in one slide, we try to batch into 32. The batch into 32 is just to say, okay, when we do the training, we are going to process the 32 image at the same time, but they are doing separately. We are not trying to correlate the so-called 32 image, pretending they are within the same category or within the same thing. So that's a different concept of batch. The batch, I think you are talking about probably referring to the so-called like in those time series data, those things, they may have some locality. In those cases, there are different ways to handle that. For example, you can do a sliding window, right? You can do a sliding window when each data point will not be one image. Instead, each data point is a set of image. It's just sliding window through, and as the sliding window through, when you do batch, the number of dimensions will always be increased. Like I said, the batch is a slightly different concept. The batch is just do a more like a pure, just a processing point of view, not necessary to say the underlying context or semantics they are totally isolated.
When you were saying,
go
ahead, Tom.
Is upon reflection, I think it for a classification problem, it's kind of obvious what you're doing, right? But in general question, when you find general situation when you want to find a pattern, maybe not so obvious. I need to think about it a little bit more. I think that was a premature question. Sorry about it.
I'm not sure it's premature. You may be looking at clustering problems. I think the batch Yong was talking about is the batch size that you actually trained the neural network, correct? Like the 32 or 16 entries at the time.
The keyword is train. Yeah, I was kind of jumping the gun here.
Yeah.
So sorry.
Clustering might be clustering might be a different different category. I mean, like if you do like clustering, I mean, you do have like even have different ways, not necessarily even to use neural network. For example, even to do clustering, image clustering, sometimes you can even do unsupervised way. It's not necessary to say you are going to apply neural network to do that. So they might not exactly fit into a standard neural network way where you have an input. You have input of different values like input layer, and you have output layer. So they may not necessarily translate directly into a neural network problem.
Gotcha. Thank you.
So I want to try to tie both Yong and Gunnar together, and this is a question, an open question. Yong, after seeing what Gunnar can do, can you think of anything where TensorFlow IO can help him with the data? And Gunnar, the other way around.
I mean, definitely. I mean, I see, like I said, TensorFlow I already have a support of different formats. I think in Gunnar's case, there are a lot of formats that's actually we are now exposed to. Actually, I even didn't notice that those before, like those medical records, they are very much unique. So maybe we can spend more time to do some additional implementation to make sure those formats like VCF I mentioned. I never heard of VCF, but maybe we can add VCF as one of the supported formats so that when Gunnar trying to grab VCF, he can just grab the package and then run that. He will not worry about how to process the VCF.
Yeah, I think
I'm not sure about VCF, but I'll definitely take a look.
Yeah, you probably don't want to. Can you guys hear me?
Yeah.
Yeah, I think the auto loading stuff. I mean, when I read your description about loading data for TensorFlow, it seems like really useful because we always had so much time parsing, right? So if there's anything that neural net or any other learning system can do to help auto parse, it seems like it would be hugely useful. There actually the KGCN that CNN that's on top of the graph is written for TensorFlow, I believe. So I think that the summarization and embedding function is done with TensorFlow. So we're going to start working with that more intensely. I might just bother you to see if we can, if we can collaborate a little bit. I think that would be great. Yeah. So I think when you're learning over the graph and you have a very sparse labeling on the graph, and you want to make guesses about other unlabeled sections of the graph, that would be a really useful place for like a neural net to layer it on top. And if it's already in the graph, it's not unstructured, right? We've got it structured, so the graph can, the TensorFlow can see different entities and see what their attributes are, and can maybe recognize patterns, in that structure. So I think there's a really good marriage there.
Very nice.
Yeah.
Very nice.
Yeah, and also one more thing is, even though the example I show is in tf.keras, that certainly is very straightforward, but it's also overly simplified. But TensorFlow itself it's actually a generic machine learning framework. So if we are working on things that's not necessarily related to CNN, it's still possible. But although you may have to do some additional programming, just makes this work. For example, if you say, okay, I have a cost function, I don't want to use CNN, I just want to use a cost function, take the gradient and find some of the local maxima or like local maxima, then you can always do that. It's also always possible. It's just going to take actual effort. So that's why at the beginning of the slide I mentioned that if you're just into a neural network, just into deep learning, you want to apply an existing solution to, let's say, to your application in either way. Maybe you can just grab Keras. But if you want to go deeper, there are different frameworks. Even PyTorch. PyTorch has a lot of competition with TensorFlow itself, but there's no denial in academia when people want to go deeper into neural network. They actually, at least when they try to do some publication, do different ways of layer, they just grab PyTorch. I think TensorFlow is more like sit as a little bit lower than PyTorch from that standpoint. So if you really want to do something, not even exactly the neural network way, you actually TensorFlow does provide a lot of things that allow you to implement, although it could be harder to write a function in a graph way and figure out if it works or not. But it is possible, yes. Not limited to neural network, yeah.
Okay, so I don't see anything new, and I see people leaving, so I think it's time to wrap up both talks. Again, Gunnar, I want to thank you for your presentation, Yong as
Great
well.
talk.
Wonderful presentations. Stick around, because even after the recording, we continue chit-chatting Python. Goodbye, everyone, and I'll see you next time in the Python meetup, but do stay.